What's up, guys? So in this video, we're going to be looking at the natural base E and what that is, how we use it. We're going to look at some simplifications, and I'm going to show you one real-life example of how we can use what's called the natural base E. First of all, there's a button on your calculator for the natural base E. If you have a TI 83 or 84, it's right here underneath the little caret button on your calculator, and it just shows a little E there. So let's look at what E is. E is an irrational number, much like pi. So E is an irrational number. It's approximately equal to 2.7. So just like pi is 3.14, E is approximately equal to 2.718. Anyway, here it is. But it's irrational, so that means it keeps going. That's why we're saying it's approximately equal, because it would keep going. The decimals keep going forever. And it's defined as when x approaches positive infinity, then 1 plus 1 over x to the x power approaches this, E. So E is an asymptote. But let's just look at how we could use it. So first of all, simplifying a few expressions. So let's say we're multiplying two e's with different exponents. Then we can add those exponents to get e to the 9th power. So 3 plus 6 is 9, so we get e to the 9th. Same thing when we divide. 16 divided by 4 is just 4. E to the 5th divided by e to the 4th will just be e to the 1. You subtract the exponents. So we have 4e. We can also, when we raise a power to a power, remember we multiply, so we'll have 3e multiply negative 4x times 2, so we'll have negative 8x. Negative 8x. Okay. We use e for exponential functions, so we can see that we can either have exponential growth or exponential decay. We get exponential growth when the exponent is positive. So if we have a positive exponent, something greater than 0, then we'll have exponential growth. And if we have a negative exponent, then we'll have exponential decay. So looking at these two examples down here, A and B, one of them is exponential growth and one is exponential decay. And we can see this first one, y equals 3e to the x, is exponential growth because the exponent is positive. It's a positive number. Whereas the exponent on part B is a negative 0.5, so that's going to be exponential decay. And if we graph these, if we graphed them using Desmos or graphing calculator, we would see that the second one, part B, looks like exponential decay, and the first one, part A, looks like that exponential growth. So we can always check our conclusions when we graph. All right. Now this isn't going to be a super long video, but I do want to show you one real-world example. We can see that in the world of finance. So anytime we looked at an example with compound interest in the last video, but in this video, here's another example where we are continuously compounding our interest. So this isn't compounded a certain amount of times per year. This is continuously compounded, and this is the equation that we would use. So let's say that we have an account, and let's say this is the equation that would model that account. Well, the 4,500 means that we put $4,500 in it at the beginning. Our rate is 0.04, so our rate is 4%. And we could calculate at how much we would have later. So let's say we have this account with a 4% compound interest rate, and we leave it in there for 10 years. So our A is going to be 4,500. Forgive my handwriting. Ooh, that was a terrible O. Let's try that again. Since I'm writing with a mouse. E to the 0.04 times 10 years. So our T is the amount of years that we leave our money in this account. So we could type that into our calculator, 4,500 times e to the 0.04 times 10. When we press enter, then we get that this, with only 4%, it compounds up to $6,713.21. So we went from $4,500 to $6,713 in 10 years. You might not be thinking that's very much, but I would say it's not a whole lot for two reasons. First of all, notice that our rate is 0.044%. Isn't the best rate that you can get. You can actually you can find some things that give you a little bit better than 4%. But also, we didn't leave it in there long enough. We only left it in there 10 years. So try the equation again with 20, 30, even 40 years, and see what the returns, how the returns would be different. What you're going to see is this graph right here. The longer you leave it in, notice that it just keeps climbing exponentially. So it just keeps climbing upward and upward and upward. So the more time it's in there, the longer it has to exponentially increase. So you won't be getting a linear return. You'll be getting an exponential return. So investing in things and putting your money into accounts that give you compound interest, that's a really good way to make some extra money. Anyway, guys, hope you enjoyed the video. Let me know if you have any questions, and I'll see you next time.